In 1916, this is a year after Einstein wrote his paper on the general theory of relativity, Einstein continued to think about the theoretical ideas. And he wrote a paper, which we have here, where he was thinking about the possibility that if space and time can warp and curve, then it might be the case that space and time can also ripple, right? The image to have in mind is, think of a trampoline, right? A trampoline, you put something heavy in the middle, it has a nice curvature to it. But if you have kids that are jumping all around on the trampoline, the shape doesn't stay nice and static, it ripples, it vibrates. So he was wondering whether it might be the case that space itself might be able to undergo these kinds of ripples, these kinds of vibrations. And this would be known as a gravitational wave. Now, interestingly, he wrote a first paper in 1916. In 1918, he corrected an error in the 1916 paper, and he continued to struggle with whether or not he actually believed that gravitational waves were a prediction of the general theory of relativity. And he worked on this by himself. He worked on it with collaborators, Nathan Rosen being one of them. And a couple years after this paper, where they expressed some confidence that gravitational waves were real, Rosen writes another paper where he basically says that he thinks they're all just a mathematical artifact. And I think many historians think that Einstein himself kind of had that view, that there really weren't these ripples in the fabric of space. And yet, by the 1960s, when the mathematical methods had been refined, where we could really look at Einstein's equations and extract from them the actual physical predictions with certainty, it became clear that gravitational waves were a prediction of Einstein's theory, which would mean that if you had, say, two objects, like two neutron stars, rotating around, they would so disturb the environment that they'd send out this train of gravitational waves. And that would mean, in principle, you could detect these because downstream, if you're in the wake of one of these gravitational waves, you will experience this kind of an effect, a stretching and a squeezing, a stretching and a squeezing. Now, I should say, this animation is not to scale. When you actually do the calculation, you find that for a typical astrophysical phenomenon, you'd find that the stretching and squeezing would be less than an atomic diameter. So the question is, how could you ever measure something so fine? And yet, as we'll discuss now, exactly that kind of a measurement has been achieved. And so to talk about that, let's turn to our next guest to take a closer look at gravitational waves as the lead astrophysicist in the LIGO Scientific Collaboration. She is a distinguished professor of physics and astronomy at Northwestern. Please join me in welcoming Vicky Kalogera. So thank you for being here.
Thank you.
And we'd like to get some insight into how gravitational waves have been detected, and LIGO is the facility. So what does LIGO stand for?
LIGO is a double acronym, actually. It stands for Laser Interferometer Gravitational Wave Observatory, and laser itself is an acronym. So it's a double acronym.
And what's that acronym? Oh, I didn't think I was going to ask you that.
Laser is such ingrained in my head, I don't remember the full acronym right now.
I think it's light amplification by stimulated emission of radiation, but I'm not sure.
Good, Brian.
I'm not sure.
Okay, so here's our detector. Here's our gravitational wave telescope. It's a new type of telescope. It doesn't look like your traditional telescope, does it? So it has this corner station where you can see it there. And then it has these tubes. And it's like tubes of a regular telescope, except these are on the ground, and there are two of them. And from the corner station, we shoot down lasers at right angle, and they travel down these 4-kilometer tubes, vacuum tubes, and they reach the end, they bounce off mirrors, and they come back. And we study the light, the laser light that comes together, and through the interference pattern of the laser light, we can tell whether the mirrors at the end of those arms are being shaken in this squeeze and stretch motion that gravitational waves are supposed to affect space and time, but space is what we can think about easier.
And you can actually measure shaking by atomic distances with this kind of device?
Yes, in fact, it's even smaller than that. It's smaller than 1,000th of the nucleus on the scale of the 4 kilometers. It's the most accurate measurement we have ever achieved, humans have ever achieved, anywhere in any field of science or engineering.
Now, how do you know that the shaking is a gravitational wave and like not someone just kicking the equipment or something?
There's a lot of shaking going on everywhere. And that was the reason why we didn't just build one of these detectors. We built 2 detectors, one in Louisiana State and one in Washington, really far away from one another. Because if the shaking is happening and it's affecting the one detector, and it's and it is Earth-based, then it's very hard to reproduce the exact kind of shaking, the exact kind of squeezing and stretching, and have it happen in 2 different locations, independent locations, so far away. So having coincidence, as we call it, at the same time with exactly the same squeezing and stretching pattern, it was extremely important. So we really needed to be able to claim such an unprecedented claim that we detected gravitational waves. It was really important to have observations of the exact same signal at the same time in 2 different independent locations.
And this first happened, this was the first achieved in 2015.
2015,
which got the world
September
completely,
14. Well, the world didn't know on September 14, 2015.
Some of us did.
Some of us did. That was a life-changing day for the hundreds of scientists and engineers who are members of the LIGO Scientific Collaboration. The world found out on February 11th, 2016, when we made the first announcement.
And so what was found?
So what was found is that basically 2 black holes, one in orbit around the other, were disturbing space-time, not very close to us, not at the center of our galaxy, but actually over 1 billion light years away at some other galaxy. And the 2 black holes were coming together because of the emission of gravitational waves. They were disturbing space-time around them, generating these ripples that you talked about earlier. And these ripples were traveling for over 1 billion years at the speed of light. And on September 14, they approached the Earth from the south. They hit our Louisiana detector first, and about 7 milliseconds later, they hit our Washington State detector second.
And that's what you expected, because that's how long it would take light to travel that distance.
Exactly. So there has to be a finite delay, because, of course, gravitational waves, just like light, doesn't travel instantaneously. It takes time. So the 2 black holes, as they were coming together in their orbit, losing energy because of gravitational wave emission, at the end they merged, like in this other movie as well. They merged. And I'll explain the sound in a minute, because it's not self-explanatory, I should say.
Yeah, not really.
Not everybody gets it.
Well, I did a version of this on Stephen Colbert's show, and his interpretation is God Bugs Bunny. That's how he interprets
That's
that.
his interpretation.
Yeah.
I should say Stephen Colbert is a Northwestern undergraduate.
Well, look at that.
I've met Stephen, and we have talked about the gravitational wave discovery. So the 2 black holes are coming together, and eventually they have nowhere to go. They're coming, and they're basically physically touching, except there is no actual surface. There is no hard surface.
Right.
There is that imaginary surface where light can't escape. And the 2 black holes merge into a single bigger black hole. They form a single black hole, and then that single bigger black hole settles, and the disturbance stops, and the gravitational wave signal stops. So it's a finite transient signal. There is this whole turmoil in space-time, and by the time you form the single black hole, the whole thing ends.
Now, we talk about the actual signature as shaking these devices in Washington and Louisiana by less than an atomic diameter.
Yes.
But what was that signal like when the black holes actually collided way out there a billion light years away?
I don't have that particular number for you, but it does scale as 1 over the distance. So if we take 1.3 for that first detection, if we take 1.3 billion light years away, it was that many times bigger when it was generated.
So I'm calculating.
Yes.
So that would be about 50 times the energy output of every star in the observable universe if I did my calculation.
By energy. Yes. You're quick.
I'm very quick. So the basic lesson though is it's a huge
explosion of gravitational wave energy for a very small amount of time. So the signal was 0.2 seconds, and for that
0.2 seconds when it
that lasted within our the frequency range that the LIGO detectors are sensitive to. So you should think, you heard about electromagnetic waves, and they come in different frequencies. Optical is the optical frequency range, infrared, radio waves, etc. These are all different frequencies of the same type of wave, electromagnetic waves. Gravitational waves have frequencies themselves. So LIGO can't see every single gravitational wave out there, can only see frequencies between about 20 hertz to about now maybe hundreds of hertz, let's say 700 of hertz at best.
Right.
So in that frequency range, this first binary black hole collision lasted about 0.2 seconds.
Right.
In that short amount of time, the collision and energy generated in gravitational waves outshined by a factor of 50 all the light generated by all the stars in the whole visible universe. Not visible by eye, but in the whole universe that we know of and we could ever detect.
And it just dilutes as it travels.
It does.
Right.
Yes.
So I've been asked about, because this is such an amazing discovery that you and your team, I mean, it's fantastic. But how, well, actually, can we look at the data? Because then I want to ask you a question. Can you raise the volumes? I can't really hear it. So that's the tiny signature that you're talking about.
That's the tiny signature.
So you can just hold it up there if you would. So here's my...
There's a few things to talk
Good,
about.
Please go ahead. Well, my general question is, how can that little tiny window of data give you so much insight into what the source was?
Yeah. The reason is that this scribble that we can see on the screen and the banana that you can see on the screen carries a lot of information, okay? And I'll take a few, maybe a minute or two to explain it.
Yeah.
First, let me start by explaining the significance of the sound, okay? I don't want anybody in this room to have any misunderstanding. Gravitational waves are not sound waves, okay? So don't go away telling anybody that gravitational waves are sound waves. However, we can take the frequencies. Remember I said something about 20 hertz to a few hundred hertz? If you know something about music and the frequency of sounds that our ear is sensitive to, that's about the range of the frequencies of sound that our ear is sensitive to. So we can take the gravitational wave frequencies and pretend it's a sound. It's not a sound, but pretend it's a sound, and convert it into sound, and say, what would the gravitational wave sound like if it were a sound? And this is what it sounds like. It sounds like a bird's chirp, whoop, which is not quite what you heard, but that's how it came out of my mouth.
But can I ask you one question on that? one question on that. So it's laudable to be clear on that, but just to also be clear, if our eardrums were able to vibrate via the gravitational wave influence, if, then that is what we would hear.
Kind of if.
Okay.
There is one distinction, if I may, that...
It's not a transverse wave?
Exactly.
Okay.
So sound waves are transverse waves, so the oscillation is along the direction of propagation. Gravitational waves and electromagnetic waves oscillate perpendicular to the direction of propagation. Okay?
Right.
And that kind of has, it's important for how it affects our eardrum.
Physiology.
Yeah, exactly.
Good.
If we go back to the image up there, the oscillation that we measure, how the mirrors at the end of that L-shaped telescope are being displaced, are basically recorded by the scribble we can see at the bottom of each banana. The two graphs are what we measured at the two different detectors. Hanford in Washington, Livingston in Louisiana. So we had, the signal was detected independently in the two detectors at the same time with only a slight time delay, as I said. And what you see in the signal, the real data is the scribble. So we see that the oscillation of the mirrors increased as time progressed. The duration, the axis under that scribble is not shown, but the duration is those 0.2 seconds. The amplitude went up, as you can see, and then it went down and petered off. That's when the two black holes came together, formed a stable black hole, and then there were no more gravitational waves. All right, so that's one thing. The amplitude went up. The sound you hear becomes louder before it dies off. The second thing is that the peaks of each oscillation come closer and closer together. That means the frequency of the oscillation is increasing, and that's the pitch of the sound is becoming higher and higher. So that's the chirp.
Great.
So that's what we call a gravitational wave chirp. The banana you see is another way of representing the exact same phenomenon. The banana gets brighter. That's the amplitude of the stretching becomes stronger and stronger. And the frequency goes up as a function of time, and that's how you get that curvature. And the closer the two black holes are coming together, the faster the frequency goes up until it dies off, because you form the single black hole.
Right.
All right. Now I'm going to finish by coming back to your initial question. What we measure is the amplitude of the wave, the frequency of the wave, and the fact that that frequency of the gravitational wave is changing as a function of time. So we're measuring a frequency derivative. These three pieces of information are encoding the masses of the two black holes and how far away this system was. So that's how, by studying that progression, that scribble as I call it, and comparing it to templates we have from Einstein's theory of general relativity.
Tell us about those. What are the templates?
If we take Einstein's theory of general relativity and ask ourselves, if two black holes are at some distance and we follow space-time and we solve with general relativity equations the change in space-time as the two black holes are moving, as the egg beater is messing up space-time around them, we can calculate what is the amplitude, the frequency, and the frequency evolution with time of the gravitational waves being produced.
Calculate with computers.
So supercomputers, in fact, because this calculation, this simulation is very, very hard, tough to do, and you need supercomputers to do it, and some of these simulations may run even for months at a time. But we, the royal we, this is actually not my own personal work, but relativists have been able to do these simulations for about a little over 10 years now. So we can create templates of these kinds of signals, and when we correlate them with our data from the detector, we can then find the best fitting template that then tells us that that particular signal came from a pair of black holes that is that far away, and the masses in this particular case was about 20 or 30 solar masses, plus or minus. Of course, there's always errors in every measurement we make.
So that was 2015, 2016. So there have been discoveries since. Can you give us a sense of what's been going on the last couple of years?
Yes, so since that first one that shook our world, and honestly, it shook humanity, if I may say, because on that day of the announcement, we were media people at all the universities did the count, not ourselves. But on that one day, we were on front covers, more than 900 newspaper front covers across the whole world. Now we have announced another 5 or so more collisions of black holes that we have detected in our data. And a third gravitational wave detector in Italy has joined operations. So now there's more confirmation of more of these events, independent confirmation. And now we're discovering a population of binary black holes in the universe.
Now, you've also gone beyond black holes.
Exactly.
Yeah.
And that has made, again, that's sort of the second most significant detection, which is 2 neutron stars.
Quickly tell us what a neutron star is.
Oh, yes. And I'm gonna tell you what a neutron star is. And have you all in New York look at the Chicago skyline, since Northwestern is in Chicago. So, so this is to scale, unlike his movie. So this is the Chicago skyline. So a big city, about 10 miles across. And the shadow you see hanging above the Chicago skyline is the edge of a neutron star, to scale. Now, a neutron star is the death remnant of a star that may be 10 times the mass of a sun, will end up forming when it runs out of nuclear fuel. So it will form, it will be about, the death remnant will be about 1.5 times the mass of the sun, and it will be about as big as a big city downtown. Okay, that's roughly the scale. You can imagine how big the circle is. Thankfully, no neutron star is hanging above Chicago as we speak, or above New York City. But that gives you some sense. So our second biggest discovery, which reached us on August 17, 2017, so we're approaching the 1-year anniversary soon.
That was right around the eclipse.
And that was another memorable day, of course, for many of us. So it was just a few days before the eclipse. Now, it used to be that the big event of that month was going to be the eclipse. And if this had not happened, I would remember the date of the eclipse. But right now, I forgot the date of the eclipse.
August 21, I think.
Thank you.
Yeah.
Because what I remember is August 17th.
Yeah.
So 2 neutron stars came together in a similar fashion. The 2 neutron stars came together, and we got another banana, except this time we had 3 detectors. So you see again Hanford, Livingston, and we had the Italian detector operating as well. And we saw the 2 bananas in the 2 detectors. The scale, you see the signal duration is much longer. It's no longer just a fraction of a second. What you see on the screen is about 30 seconds. But actually, in our data, this is what you see visually here. But in our data, we extracted, the signal lasted 140 seconds, so a couple of minutes, so really long signal, which tells us that the masses that came together in this death spiral were actually much smaller.
Right.
So about 1.5 solar mass.
As opposed to 30 or so.
As opposed to 30. So the lower the mass, the longer the signal, the longer this death spiral lasts. Now, the third detector doesn't show a banana, partly because the third detector is not as sensitive, and partly because it was at a very special location on the sky that the third detector didn't have good visibility, let's say. And then spectacular things happened after the collision of the two neutron stars. Unlike two black holes, which come together in peace, form a single black hole, and nothing else happens after that, two neutron stars actually give us a whole set of fireworks in electromagnetic waves.
So you could actually not only see them in gravitational waves, you can see them.
Yes, you can see them in light, in
Right.
real light. And that started a whole other type of astronomy, multi-messenger astronomy. Multi-messenger meaning two types of waves came out of the same source, gravitational waves and electromagnetic waves.
And what have people learned from the neutron star collision? There's a lot of talk about new ways of thinking about nuclear astrophysics.
Yes, so we learned a couple of different things. So first of all, we learned things from this multi-messenger character of the source. So one thing is that the first thing we saw in electromagnetic waves was a gamma ray signal. This is the highest frequency electromagnetic waves we can detect. And we knew gamma ray, short bursts of gamma rays existed. We had detected them for many years, since the late 60s. And we had hypothesized that maybe mergers of neutron stars were responsible for them, but we had no proof. The proof came from the gravitational waves, because only in the gravitational waves we can measure masses. So the measurement, that chirp, the banana, tells us that it was two neutron stars that collided. So we've associated with, for the first time, we had proof that two neutron stars collide can give you a gamma ray burst. So that multi-messenger combination proved the origin of short gamma ray bursts are due to neutron star collisions. That was one big discovery.
Yes. Yep.
The second was that the two neutron stars came together, and as the neutrons collided, they actually formed the heaviest elements we know on Earth. So elements like gold and platinum, a lot heavier than iron, we of course know they exist. We have them on our planet. We have them, on our rings and earrings or whatever.
I lost my wedding ring, so I used to have one of those.
Does your wife know?
She does.
Okay.
It's a bit of a sore point, but let's move on.
Okay.
Yeah.
So we know they exist, but actually, astrophysically or physically, we didn't know for sure how they are formed. They are not formed in the centers of stars. That we knew, and through nuclear reactions. So a hypothesis was maybe they're formed in neutron star collisions. With this one event from August 17th, we got experimental proof through the electromagnetic waves and gravitational waves telling us two neutron stars collided. We have now proof that gold was formed at this one event.
Right.
And therefore, we solved that mystery as well.
That's fantastic. Congratulations.
Well, I take credit, not just myself, but
The
there is
whole
a
team,
whole
I understand.
collaboration of hundreds of scientists.
Absolutely.
Yes.
So we're reaching the end of our segment, but there's one other question, or maybe 1.5 questions. So have you received any data that doesn't fit the templates? Or more generally, how can you imagine testing Einstein's general relativity in this extreme environment using gravitational waves?
We always try to test Einstein.
Yep.
Okay. We pushed that frontier. He made, his theory must break down at some point, because it involves the singularity at the center of the black hole, and we don't like singularities.
That's where the math just breaks down.
Exactly.
Yeah.
That's where the division by zero doesn't make sense. So somewhere, general relativity has to break down. With gravitational wave observations, we are observing black holes moving at half the speed of light, 60% of the speed of light. This is the strongest regime of gravity we have ever probed with anything. Nothing else has probed that regime. So, so far we have not seen anything in the gravitational wave data that disagrees with general relativity, but we keep pushing that frontier, and maybe one day we'll see something. So it's always at the back of our minds.
And would you say that sort of would be the culmination of this enterprise to to push the understanding of gravity to the next place?
The physicist in me might say that, so that's always something we try to keep testing that theory. The astrophysicist in me wants to know about these black holes and neutron stars. How do they form?
Right.
What's their masses? How can nature form these pairs of black holes and neutron stars in such high numbers that we see so many of them?
Right.
So this is what we're after on the astrophysics side.
Well, good luck with all those fantastically interesting projects. And everybody, please join me in thanking Vicky Kalogera.
Thank you. Thank you, Brian.
Thank you.
Take care.
Fantastic.